All right, welcome back again. Today we're going to be doing section 6.7, and this is where we're going to talk about the hyperbolic functions. So the first thing I'll say is fair warning, there is a ton of information packed into this one section. There's just so much information packed into this one section. I won't require you to memorize much of it, but you really should remember that these functions exist because they do pop up a lot. And if you're interested, someday you can ask me and I'll tell you a story about how one of these functions popped up in an unexpected place and my colleague recognized it. So it's another good reason to work in groups and just a reminder of why we should work in groups and the importance of peer review and frankly just sharing scientific discoveries with other people so that way, they can help you figure out your own problems. Okay, so this section is all about the hyperbolic functions, and there's a ton of stuff to go through. We'll go through the definition of these functions. We'll look at the graphs of these functions. We will talk about hyperbolic identities. We will go through the derivatives of these functions. We'll talk about the inverse hyperbolic functions, and then we'll talk about the derivatives of the inverse hyperbolic functions. So in a very uh, in a very real way, I guess you could say that this is I'm going to be introducing you to a new type of function, a new class of functions, and we're going to look at all of the things related to them. So it's kind of just like cramming everything into one section. So that there's a lot. All right, here we go. So let's just start with the definitions. Um, Oh yeah, here we go. So how did these things come about? Well, it turns out that certain combinations of the exponential functions e to the x and e to the negative x arise a lot. So combinations of these things, basically sums and multiples, arise in so many ways that we give them special names. So where did these functions come from, or why are they called this? Well, they're related to sine and cosine functions because of the geometric interpretation. So they have the same relationship to the hyperbola that the trigonometric functions have to the circle. So if you remember from trigonometry, the way that you define sine and cosine is as the vertical and horizontal displacement of this point on the unit circle, right? So this length right here is sine, and this length right here is cosine on the unit circle. So that's how you define sine and cosine. Well, the hyperbolic sine and the hyperbolic cosine, and then by continuation, the hyperbolic tangent, those are defined as this point on the hyperbola. So it's basically the horizontal displacement and vertical displacement of this point, but this point is on the hyperbola x squared minus y squared equals 1. So usual trigonometric functions are all about the unit circle. They're derived from this relationship and the vertical and horizontal displacement. The hyperbolic trigonometric functions are derived from this hyperbola, which is given by this relationship, and they're defined as the vertical and horizontal displacement of that point. So that's why they have that name, hyperbolic sine, cosine, tangent. So what are the actual formulas? Now that we've seen the geometric interpretation of them, what are the formulas? It turns out these are the formulas. So we defined hyperbolic sine as e to the x minus e to the negative x divided by 2. And then hyperbolic cosine, e to the x plus e to the negative x divided by 2. Sometimes this is called sinh, and this is called cosh or cosh. Um, and I'll say this right here, these you do need to memorize. You need to memorize these two formulas. So when somebody says sinh x, you should be seeing in your head e to the x minus e to the negative x over 2. And when somebody says cosh x, you should be thinking e to the x plus e to the negative x over 2. All right? And I say this little note down here too. If you are wondering why, why there is the presence of e, that's something that you make clear in a complex analysis course. So we will not be able to do that here in this course, but many of you will later on, and you'll be able to see the intimate connection between E and these formulas right here. Okay, so here's some other definitions. Now that we know what sinh and cosh are right here, from those we can define all of the other 6 hyperbolic trigonometric functions. So what is tanh of x? It's sinh over cosh. What is cosec? It's 1 over sinh. What is sich? It's 1 over cosh. And what is cough? It's cosh over cinch. I'm half making up the pronunciations of these things. So if I'm not pronouncing it right, or if you've heard it pronounced otherwise, that's okay. I'm just kind of making a guess at it. In the end, they're technically called hyperbolic this, hyperbolic that, hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent. So that's the proper way of pronouncing them, is by saying the full word hyperbolic as fast as you can. Okay. So these are the definitions. And this is also why I say you need to memorize these two. Once you have those two memorized, you get all 6. You get the other 4 for free. Now, what do the graphs look like? So this is something that's pretty cool, actually. So if you want intuition for the graphs, the intuition can come from graphical addition. And this is something that I hope one of your teachers or professors in the past got to talk to you a little bit about directly. But if we want to construct functions, or if we want to visualize a sum of functions, for example, you can do it geometrically because you're adding outputs. So let me zoom in on this one for a minute. In this picture, this curve right here, that's the graph of hyperbolic sine. And if you're wondering how you come to that graph, like where do you get that graph, it's because if you remember, you're going to add up 1/2 e to the x and negative 1/2 e to the negative x. So maybe I should write this right here. Remember, sinh was e to the x minus e to the negative x over 2. Well, this is e to the x over 2 minus e to the negative x over 2. But e to the x over 2 is half e to the x. And negative e to the x over 2 is negative 1/2 e to the negative x. So what this is saying is, if you want to produce this graph for sinh of x, you're going to add the outputs of these two individual functions right here. So let me clear some things up. Let me erase this, and I'll draw it with my pen, right? So what is the value of sinh at this point right here? Maybe I'll use a different color, actually. Let me get to blue. Here we go. No, I'll use red. Why not? Okay. So if I pick this x value here and I want to know what the value of sinh is, or hyperbolic sine, I take this height and I add it to this height. And when I do that, I get this point right here. Maybe I'll use a different color for that. I get this point right here. That's the value I get when I add this height and this height. And that's what you do for every single point. That's actually just what graphical addition is. You're just adding the outputs at every single point. Think about this one right here. How do I get this point when x is equal to 0? Well, I add this length and I add this length. But this length down here, it's negative, or I should say this displacement, right? This displacement down here is negative, and it has the same size as this one right here. So when I add those together, they cancel out, and I'm left with 0. There we go. So that's where these graphs are coming from. You're basically just adding up this function, you're adding up this function and this function at every point, and when you do that, you get hyperbolic sine. Okay, same thing for hyperbolic cosine. You do the exact same thing. Hyperbolic cosine is this curve right here, right? How do you get it? You add up the values of that curve, and the values of this curve right here. And when you add those up, that will produce hyperbolic cosine. Pretty cool. And then same thing for tangent. Oops. Oh, sorry. So tanh. How do you get tanh? Well, you basically just do the ratio of sinh over cosh. And then when you do that, you will get all these results here. Notice that it looks a lot like arctangent. But it's not the same. It is a hyperbolic tangent. But again, this is another function that we really, really like because it's bounded. It's defined for all real numbers, and it's bounded between -1 and 1. That's an awesome property to have. Okay. All right, so now we've got the definitions for all of the hyperbolic trig functions. We've seen the graphs. Now we get some identities. You do not need to memorize these identities, although some of them you'll probably just remember by chance. probably just remember by chance. So sinh of negative x is negative sinh x. In other words, hyperbolic sine is an odd function, right? Odd function. Oops. Odd function. Cosh of negative x equals cosine cosh x because this is an even function. So the even odd properties of the hyperbolic trig functions are the same as the even odd properties of the trig functions. There's a related Pythagorean identity. It's this one right here. Except now instead of it being plus, it is minus. There we go. There's also a tangent identity. So maybe this one's a tangent identity. Here we go. 1 minus tanh squared equals sech squared. Very, very similar, except now this is a negative and they're hyperbolic instead. And then you also have these angle sum formulas right here, angle sum formulas for sinh and cosh. Like I said, you do not need to memorize these, although I will admit that these are kind of nice to recall, but you don't need to have them memorized. Okay, let's prove one of these identities. Let's prove the related or the associated Pythagorean identity here. So we're going to prove this one. And this is one I actually want you to think about how to prove first. So try to think about it for a moment. How would you prove this on your own? What could you do first? Say something out loud now about what you would do first to prove this. All right, and then try to work it out on your own, and then we'll work it out together in just a moment. All right, here we go. So I would say if we had to prove this identity, a very good place to start would be the definitions of these two functions, the definition of cosh and the definition of sinh. Let's just start with that. So when I plug in these definitions, the formulas, right, I get this and this, just by the definition of what they are. Now I'm just going to go through some algebra. The algebra is not too bad. You just FOIL out the numerators. And then you'll get some really nice simplifications and some cancellations. You'll get the e to the 2x's cancel. You will get the e to the negative 2x's cancel. And then here you're going to end up getting 2 plus 2. Remember, there's a negative right here. So this is negative 2. So you get 2 plus 2 equals 4. Then for the denominators, those are both 2 squared, which is 4. So we get 4 over 4, which is 1. And there it is. There's the proof. Okay. All right, so now we've got the definitions, we got the graphs, we got some identities, we proved an identity. Haven't done any calculus yet. So we haven't done any calculus yet. This is all more like a pre-calculus content. So now, here are the derivatives. We are not going to prove all of these. We're going to prove one of them. And the rest I leave to you as an exercise if you would like to try them out on your own. But here are all the derivatives. And you'll notice some very nice relationships. So for one, the derivative of sinh is cosh. In this case, this is similar but not the same as the trig functions, but the derivative of cosh is sinh. So it's not the opposite in this case, it's just sinh. So these things are basically almost like more intimately connected than the regular trig functions. The derivative of tanh is sech squared, so you still have that analogous relationship. And then these other ones too. You have analogous relationships to the derivatives of the trig functions themselves. So you get all of these. There's all the derivatives. We're only going to prove one. We're going to prove the first one. So let's do that right here. We're going to prove that the derivative of sinh is cosh. And I want you to think about how you would do this one again, or do this one, I should say. So think about how you would start. How would you prove that this is the derivative of sinh? All right, remember to say something out loud to yourself about how you would do it. What would you use to prove this, to compute that derivative? All right, now try to work it out on your own and we'll do it together in a moment. Okay, here we go. Let's see. I would say that a good place to start is the definition. Let's start with the definition of sinh and differentiate that. So here we go. Sinh is e to the x minus e to the negative x over 2. So now we can just compute the derivatives, and we already proved what the derivative of e to the x is. It's just e to the x again. So we can do that. We're going to have to use the chain rule when we differentiate this. So we'll get e to the x minus -1 times e to the negative x over 2. And then when we do this simplification here, we get a plus. And so we get e to the x plus e to the negative x over 2, which is cosh. Easy peasy, right? Not too bad for that one. Again, I leave the others for you as an exercise. I'm sure, like, you might as well just try it now. Try to show that the derivative of cosh is equal to sinh. It'll probably take you like maybe a minute or two, but you'll see that it also comes out that way. All right, let's do this example. So this one is another one I want you to try on your own, and then we'll do it together. So try to compute this derivative. And I think this one I'll jump straight to the writer, the thinker and the writer. So think about how you would do this, and then try to compute it on your own, and we'll do it together in a minute. All right, here we go. Let's see. We're definitely going to have to use the chain rule, and we're going to have to do derivative of this with this left alone, and then we'll have to do the derivative of the radical with the inside left alone, and then we'll have to do the derivative of the inside. So we've got a 3-link chain here. But we can do it. You just walk through, mind your P's and Q's, as they say, and use the chain rule. So the derivative is going to be, derivative of cosh is sinh, inside left alone, times the derivative of the inside, which will be this, with the inner inside left alone, times the derivative of the inner inside, which is -2x. So this is the derivative, and then you can kind of clean it up a little bit. So when you clean it up, you get this. Oh, I just realized I could simplify this more. Yeah, I could cancel these 2's. There you go. Maybe I should do that in the slides. Cancel those 2's, and you get something that's even a little bit nicer. All right. Okay, so now, okay, moving right along, right? So we got all these, we just talked about derivatives. Now we've got to talk about the inverse hyperbolic functions. Inverse hyperbolic functions. All right, here we go. So anytime you talk about inverse functions, you need to carefully consider domains and ranges, right? Just like we talked about in the last section. You really got to pay careful attention to the domains and ranges involved. So here's just a repeat of the graphs of these functions. And the reason I wanted to repeat them is just by inspection, you can see that sinh is already 1-to-1. It passes the horizontal line test, which means it's invertible. That means we don't need to restrict the domain or anything like that. This is an invertible function. Same thing for tanh. So tanh passes the horizontal line test. We don't need to restrict the domain. It is already invertible, and we can find its inverse. The one that we have to restrict the domain on is cosh. So here you can see that cosh does not pass the horizontal line test. So it's not invertible outright. Not invertible outright. The only way to make it invertible is to restrict the domain. And just by looking at the picture, you can probably make a pretty good guess about what we're going to restrict the domain to be. Anyway, how we're going to restrict the domain. We're going to restrict it so that it's just this part of the graph right here. Here we go. Oh yeah, I say it right here. There we go. So the only one we're restricting is cosh, and we're restricting it to 0 to infinity. Here we go. So just like I had done in the previous section, here's just kind of a list of the functions, their domains, and their ranges. So sinh, domain is all real numbers, range is all real numbers. Tanh, domain is all real numbers, range is -1-to-1, right? Remember this, -1-to-1. Okay? And then cosh, we have a restricted domain, but the range is going to be 1 to infinity. And again, you can see that right here. Here's the range from 1 to infinity. And just like I had mentioned in the last section as well, by performing this restriction, we're actually not losing any possible output values. So that's one of the reasons why these restrictions aren't necessarily bad ideas, because doing this restriction does not lose us any information. We don't lose any of the outputs, right? We can still figure out everything this thing spits out. Now, since we're talking about inverse hyperbolic functions, and inverse functions switch the domain and the range, they invert the domain and the range, we get this. So inverse hyperbolic sine, domain and range switched, can't tell in this case, or in this case. Inverse hyperbolic cosine, domain and range are switched. Inverse hyperbolic tangent, domain and range are switched, and that's what you got right there. There you go. So you've got arc sinh, arc cosh, and arc tanh. Okay, here is what the graphs of those functions look like. So arc sinh looks like this. Don't be confused about arc sinh. It is not asymptotic to any finite numbers, so it's not bounded like arc tangent was or like tanh was. So this will keep going up and up, and it will go to infinity. So there's no asymptotes. It does not have any horizontal asymptotes. Here's arc cosh. You can see that it's been just tipped onto its side, right? Because you reflect across, you reflect across the diagonal, right? And you'll get that thing. And then same thing with arc tanh. We basically reflected this across the diagonal and we get this. All right, so those are the graphs. Those are the graphs. Now, we have seen what these things are. We know that they exist. Like we've seen the graphs, we know that these things exist, but what are the actual formulas? What is the formula for inverse hyperbolic sine, inverse hyperbolic cosine, inverse hyperbolic tangent? How do you find the actual formula for these things? Well, maybe not surprisingly, you could imagine that you just solve the original formulas for the input. So I didn't do this in the last section, and I didn't do it in this section, but I do it in my lectures on inverse functions. If you want to invert a function, you just solve for the input. So let me flash back for just a moment here. Wait, what slide am I on? Okay, that one. Let me flash back for just a moment. Here. If I wanted to invert the hyperbolic sine function, then all I need to do is solve for x. Solve for x. Doing it requires a little bit of cleverness and a little bit of algebraic manipulation, but it can be done. You just have to, if I'm not mistaken, you need to use one of the most powerful techniques in math, except in this case, I believe you're going to use adding 0. So if you add 0, but you add 0 in just the right way, I believe you'll be able to factor this, or complete the square in some sense. Okay, we're not going to do that here. We're just going to give the formulas, and then again, I leave that to you as an exercise if you would like to try it. So here are the formulas. When you invert the hyperbolic sine function, this is the formula you get. So sinh inverse is ln of x plus square root of x squared plus 1. There you go. Makes sense that natural log is involved, right? Because the sinh function involves the exponential. So it makes sense that the log would be involved in its inverse because the natural log is the inverse of the exponential. Same thing for cosh. Notice they're very, very similar formulas, but they're not the same. And then for tanh, you get this. And then here are the domains. So x is any real number. X has to be greater than or equal to 1. And then x is between -1 to 1 exclusive. Again, I will not go through and derive these formulas, but I encourage you to try to do that on your own. It's actually pretty fun. But we are going, oh wait, no, I am going to prove one. Yes, okay, I am going to prove one. Yay, okay, we'll prove the first one and see if I remembered correctly. We're going to prove that this is the formula for inverse sinh. And then I leave the rest as an exercise. Here we go. Okay, so what do I do here? Oh, okay, looks like I'm not adding 0, but I am being a little bit clever, and I am writing it as a quadratic. That's right. So here's how we do this. Since we're dealing with inverse functions, a good place to start is to just give them a name. So let inverse hyperbolic sine be equal to y. Then by definition, we know that sinh of y is equal to x. And then now we can just use the formula for sinh, right? This is one of the reasons you always, you do this little like naming convention here, because then you can use the original formulas that you do know. So this is sinh of y. And what we need to do is we need to solve it for y. That's basically the goal here. We want to solve this for y. So here's what we're going to do. Multiply both sides by 2. So that becomes 2x. And then we've got this. We're going to move everything to one side. We're going to treat this as a difference function instead, right? And then here's where we're going to be a little bit clever. Multiply both sides by e to the y. And when you multiply both sides by e to the y, you're going to get e to the y squared. And then here, e to the negative y times e to the y will just become 1, because you'll have e to the 0, which is 1. And then here you have a mess still. You have 2x times e to the y. But here's the clever part. Here's the clever part. This equation is quadratic in e to the y. It's a quadratic equation where the variable is e to the y. So because it's quadratic, we can use the quadratic formula. Yay! Everyone's favorite, right? We can use the quadratic formula. Plug in what we know the b value is, plug in what we know the a value is, plug in what we know the c value is, and this formula will give us the roots to this equation. So here we go. Let me label some things. A is equal to 1, b is equal to negative 2x, and c is equal to negative 1. So quadratic formula, which you should remember, it is this. B squared minus 4ac all over 2a. There we go. That's the quadratic formula. When we plug things in, we get this result right here. Right. Now, we can factor out a 4 from each of these terms under the radical, and then pull it out of the radical to make it a 2. And then each one of these terms has a 2 in them, so we can cancel those. And then we're left with x plus or minus that. So notice here we have e to the y equals this. E to the y equals this. And again, we have to include the plus minus and then eliminate a case, which we're going to do right now. We know that e to the y is always positive, right? It's just an exponential function. Remember, the graph looks like this. It's an exponential function. It's positive for all values of y. That means that the negative result will not be valid. So we're going to toss out the negative case, and we're going to keep the positive case, like so. One last step, write it in logarithmic form, and we're done. So we get y equals ln of x plus square root of x squared plus 1. And that's inverse hyperbolic sine. That's the formula. There you go. Woohoo! Okay, so we proved one. That's a fun proof. I recommend you try the other one. See if you can prove this one. See if you can prove, go back, this one. Try to do this one on your own using the same techniques, and you'll see it's not so bad. It's pretty much the same argument, except you'll have the formula for cosh instead of sinh. All right? Whew, okay, so now that we talked about the inverse hyperbolic functions, we got their formulas, we proved one of their formulas, now we can talk about the derivatives of these functions. That's right, the hits just keep coming. I told you, this one section just has so much information packed in. I swear you could spend multiple weeks on just this one section, but we do not have that much time. Definitely do not have that much time. So here are the formulas. I'm not going to prove any of these formulas. I just double checked, but here's what they are. You don't need to memorize these formulas. I would give you these formulas on the test, but it's good to at least know them and look at them and think about how they're related to the derivatives of the inverse trig functions that we saw in the last section 6.6. But here they are. Here's the derivative of inverse sinh, derivative of inverse cosh, derivative of inverse tanh. Notice how similar they are to the derivatives for the inverse trig functions. Remember, the derivative of arctangent was 1 over 1 plus x squared. So there's all this, there's this beautiful connection between the two. The formulas are so similar. All right, but this is all of them. So this is all of the derivatives of those 6 inverse hyperbolic trigonometric functions. Let's just practice with one, all right? So this is one I want you to try on your own. So see if you can compute this. Think about what you would use first. All right, now say something out loud about how you would do it. What do you think you're going to have to use? All right, now work it out on your own, and then we will do it together in just a moment. All right, here we go. So one thing I can see right away is we're going to have to use the chain rule because we have a chain. We've got a composition of functions here. So we're going to have to do the derivative of inverse tanh with the inside left alone times the derivative of sine using the chain rule. So let's see what we get. All right, the derivative of inverse tanh is 1 over 1 minus x squared, but we leave the inner function alone, times the derivative of the inner function, which gives us cosine. So we have cosine x over 1 minus sine squared x, but using the Pythagorean identity, 1 minus sine squared of x is just cosine squared of x. So we get cosine over cosine, which is 1 over, oops, whoa, 1 over cosine, which is equal to secant. So it turns out the derivative of this is secant x. Not too bad. All right, so we talked about the derivatives. Next, we can talk about the integrals of the hyperbolic functions. Okay, so this one I want you to try on your own as well. I'll just do this right away. So think about how you would start it, and think about what inverse hyperbolic function you're going to need to use, and then we'll do it together in a minute. All right, now let's do this one together. First thing I notice is that we do have a definite integral, so our end result will be a number. It will not be a function, it will just be a number. This structure, I believe that looks a lot like inverse hyperbolic sine, but I can never remember. Is it inverse hyperbolic sine or inverse hyperbolic cosine? Let's go look. Here we go. Look, this structure is the derivative of inverse hyperbolic sine. So we're going to use that for sure. In fact, I believe that is just the formula for inverse hyperbolic cosine. So there we go. This, oh, I'm sorry, I should say this, when we integrate the derivative, we get the original function back. We're just going to evaluate inverse hyperbolic cosine at 1 and 0 and take the difference, right? We have formulas for these. So when we plug this into the formula, we get this. That's what we get. All right. And then next, let's play. So there we go. You made it through. I know this is a somewhat like medium length lecture, but OMG, it is just packed with so much information. Like I said at the very beginning, these are functions that do show up pretty frequently, especially in certain applications. So if you're looking to go into like engineering, like mechanical engineering and stuff, there's a good chance that you will use these inverse hyperbolic functions and just the hyperbolic functions in general. So it's good to know that they exist, and it's good to know roughly what the formulas are, but I won't require you to memorize much except the formulas for cosh and sinh, and that's kind of it. Once you have cosh and sinh, even if you wanted the derivatives, you could just compute the derivatives using the formulas. So make sure you do know those formulas. All right, well, I'll stop right there. So thank you all again for listening, and I will see you next time.